Hi there! Welcome to a new physics lesson filled with adventure and discovery. Today, I will be introducing you to this idea of heat, or this idea of transfer of energy due to a difference in kinetic energy. We're going to talk about temperature, we're going to talk about heat, we're going to be talking about the different units that we can use to measure temperature or kinetic energy, and then we will also be ending our adventure time with the different kinds of heat transfer. How do objects transfer heat between each other? But first of all, I want to propose a question. What does temperature actually measure? If you think about that and you try to answer in your head, the first thing that comes to mind will probably be well, temperature measures heat, which is sort of true. But today we're going to look at that a little bit more deeply. So let's get started. First of all, temperature. Temperature, we're going to say, is not actually a measure of heat, but actually it's a measure of kinetic energy, or how much movement there is in the molecules that is in a certain object. And a couple of other things about temperature. The more temperature something has, or when we use the word hotter, the hotter the hotter an object is, the more kinetic energy that object has in its particles. And so, for example, when we talk about water, and if we heat up water, if we start boiling it, if we increase the temperature of it, the water molecules will start moving faster and faster and faster until eventually the molecules of the water will have enough energy to turn into a gas phase or to evaporate. Okay, so temperature is not really the measure of heat, but rather how fast are these molecules moving, how much motion is there inside of that object. So moving on, that temperature is different to what we call internal energy. And so internal energy is all of the energy, kinetic, potential, maybe even a little spring potential energy inside of an object. And so we use the variable U to define internal energy. And so as you notice, if we were to zoom down to the molecular level of an object, it looks something like this, where all the molecules are kind of bouncing off of each other, and they all have some kind of potential or kinetic energy. Okay, so we're going to be using these terms in this chapter. But some other things about when we're talking about energy and temperature, if I were to have a hot object and leave it in this cold room with the AC, eventually, and you guys can verify this, eventually that object will become the same temperature as the room. If I put an object in a basin of water or a bucket of water, that object is going to eventually become the temperature of that bucket. So we call this thermal equilibrium, where the temperature of the objects will eventually reach this balance point, or this equal point. Or in other words, the heat will flow from hotter object to colder object until we have the same temperature. And so another good example of this is if you buy like a Frappuccino from Starbucks, eventually it will cool down. We have things that will slow down that process, but eventually it will become lukewarm, just like the room temperature. Another interesting thing about heat and temperature is that when we heat up an object, when we increase the temperature, we add energy into the object, the molecules in the object will kind of space out and will cause the object to expand whenever we have. So here's a really interesting picture. Across the continental United States, railroad tracks can have this tendency to curve because of the massive hot temperature that is reached in these different areas. And why is that? Well, it's because the molecules, the metal, is expanding whenever it gets hot. Same thing with concrete. Concrete, if you look at sidewalks or even roads, there are gaps every so often, and that's why you hear the dunk, the dunk, the dunk, the dunk when you're driving along. And the reason for that is because when it gets hot, the concrete will expand, and so we need to leave some room for that expansion. So we call that thermal expansion, expansion due to heat or temperature. So how do we measure temperature? That's our next topic. We have a bunch of different variables we could use to measure temperature. two of the most used ones in the United States is, of course, Fahrenheit, and then we also have Celsius, which is the SI unit for temperature. And so we have these two equations that we can use to easily convert between Celsius and Fahrenheit. Celsius, by the way, is a measurement of temperature that's based upon water. 0 Celsius is freezing water, 100 Celsius is boiling water. And so Celsius is totally based upon water, and that's why we use it as SI unit. It's a pretty easy unit to use. The body temperature Celsius is 37 degrees Celsius, and then of course boiling room temperature is about 22, 23 Celsius. And so you might see that used elsewhere in the world, like Japan or in Europe, they use Celsius. However, we use Fahrenheit. There's a really interesting video, TED video on Fahrenheit. You guys can watch a little bit later, and how they think we came up with that Fahrenheit. But if you take a look, let's say I were to find I had Celsius and wanted to find Fahrenheit. What I'd do is I'd plug in 9/5 times the temperature, or Celsius. TC is temperature in Celsius, and then I'd add 32 to get my temperature in Fahrenheit. If I had the reverse, notice is pretty much just the opposite of that equation. If I had Fahrenheit and I wanted to find Celsius, I would take 5/9 times the Fahrenheit minus 32 degrees Celsius. So pretty simple equations we can use to figure out, to interchange between Fahrenheit and Celsius. A third unit we use is Kelvin. Kelvin, actually we'll talk about Kelvin later. How do we find Kelvin? Well, if I have Celsius, it's pretty easy. All I'll do is I'll take my Celsius and add 273. If I want to be super precise, I'll use 273.15 added to Celsius to find my temperature in Kelvin. Kelvin is named after Lord Kelvin, who theorized that there had to be at some point the coldest temperature possible, and so he called that 0 Kelvin. And today we call that absolute zero. 0 Kelvin is the coldest temperature possible because that is a point, and we're going to talk about this later, at which we have lowest entropy, that the molecules are not moving around anymore, but they're just staying still and vibrating. And so we would call that absolute zero, or 0 Kelvin, the coldest temperature possible. Of course, the universe is a little bit above 0 Kelvin, and so it's physically impossible to get it to 0 Kelvin, although we are able to get objects pretty close nowadays with our technology. And so this brings us to heat, because temperature is directly related to heat. Heat is a word that we use a lot in normal terms to describe the temperature, usually the temperature of things, how hot or cold. It's really hot in here, or really cold in this room. But I want us to kind of shift our view of heat, and to shift it in terms of heat being energy. Heat being this energy that is transferred, that makes molecules move faster or slower and causes a rise or decrease in temperature. And so notice heat is measured in joules. It is a value of a change-up of energy. It's another type of energy that we can play around with. And we have this transfer of heat whenever the substance, or whenever we transfer heat between objects, it will also change its temperature. So temperature is an effect of heat. Heat causes a change of temperature. That's kind of the distinction there. And so there are three main ways we can transfer heat, and certain objects, and you can notice this around you, even feeling the black tables that you're sitting at. Some objects are able to move heat a lot faster than others, and we call this thermoconductivity. Conductivity refers to being able to contain or transfer heat. And so, of course, metals are very heat conducive. They can heat up really quickly, they can cool down really fast. And as always, like we said before, heat always moves from high to low temperature. And so I'm going to go over the three different types of heat transfer. The first one is conduction. And conduction is whenever we transfer heat through physical direct contact. When we have a hot object physically in contact with another object that's heating that second object. And so we use this in cooking a lot. So for example, when you're frying an egg, that egg is physically touching the hot pan. And because of that, we call this conduction. Okay? So the hot object is vibrating, and those vibration gives off this energy to this other object, which absorbs the energy and causes its molecules to vibrate and to start moving around. Okay, so that's kind of how conduction works. The second one is convection. So convection is a transfer of heat through either air or liquid currents. So you might have heard of convection ovens. Convection ovens are able to cook things a little bit quicker because it kind of moves around the air. It has this air current within the oven, which kind of circulates the hot air and helps things to heat up a little bit faster than conventional ovens. Boiling wiener dogs, or hot dogs, is a good example of convection. The hot dogs are not, I mean, they could be physically in contact with the pan, but most of all, we're kind of cooking it in the water. The water gets hot and it also heats up these hot dogs. And so it's the heat from the liquid or gas to the object is convection. And the last one we have is radiation, this last mode of heat transfer. And this type of transfer is a transfer of heat through electromagnetic radiation. So for example, when we cook things using solar power, the sun, it's not directly required by a transfer of energy from atoms or molecules. It's through wave particles, energy to empty space. So for example, another good example is your microwave. Your microwave your food isn't cooking through these other particles rubbing against it or surrounding it. Rather, it's these wave particles, microwaves, that are coming in and that are causing this transfer of energy to your food, to heat up your food. Okay, and we're going to talk about this. We've already mentioned this a couple times, that whenever we're doing something, energy, we have to, all things obey this law of conservation of energy. So it's always transferred or lost. A lot of our energy is lost to our environment around us. But for the most part, we can transfer this energy to and for us. So here's a really good example. If I have this little paddle here and I have this little turn thing that's connected to this paddle, and I start spinning it, turning it, because I'm causing this, have this kinetic energy. I'm spinning this paddle, and it's in turn it's going to spin the water around. And notice it's also connected to these weights on the side here. As the weights move up and down to turn this paddle back and forth, or I can manually crank it, it's actually going to heat up the water inside. It's going to cause our temperature to heat up. And so what we can say then is this mechanical energy, this potential energy, this kinetic energy can be transferred into heat energy. It can raise the temperature of this water, which is pretty cool. Nowadays, we kind of use the reverse. We're going to talk about this more in the next lesson. But we can use heat energy and transfer into mechanical energy. That's how we, figured out how to have steam engines that power trains, and eventually there are gasoline engines that power our cars nowadays. So yeah, that's kind of our introduction to our heat unit, or our thermodynamics unit. And we'll see you next time. Thanks for joining us.